All right, so we're going to be looking at parametric equations again, but in this case, we're going to be looking at when they have some trig functions inside them. But the initial concepts are all the same, like how to get the Cartesian where we substitute the t variables, or when we're trying to find the range and domain of the functions. We can find the ranges of x and y. So that's all the same. The only difference is when we're finding a Cartesian, rather than substituting like we did before, when we're dealing with trig functions, we have to actually look at trig identities. So that's the only difference between non-trig and trig functions when we're dealing with parametric equations. So let's take a look at this one here. We have x is 1/3 sine t, y is sine 3t, t is between 0 and pi/2. And it says show that the Cartesian equation is in this form. So normally we would say, oh, let's rearrange for t and then substitute it in. However, for trig terms, rather than doing that, what we're going to do is think of an identity linking the trig terms together. So I can start off with y is sine 3t. So this is where you have to be very knowledgeable or very familiar with the trig identities we looked at in the previous two chapters, like the compound angle formula, the double angle formula. All these identities, you need to be very, very well rehearsed with it, because you need to know which one to use when dealing with this kind of stuff. So when I see sine 3t, then you can think of, oh, we can maybe split it up into sine 2t plus t. Therefore, I can expand it using the compound angle formula. So we'll have sine 2t cos t plus cos 2t sine t. We're left with sine 2t and cos 2t, so I can expand that as well, right? So this will be 2 sine t cos t plus, now cos 2t, as we said, looked at the previous chapter, there's like 3 variations there, right? However, if you look at what x is in terms of sine, so we'll probably have to write it in the sine form. So this will be 1 minus 2 sine squared t times sine t. Now it's just a matter of simplifying it. So 2 sine t, this is cos squared, so I can rewrite it as 1 minus sine squared because we want everything in terms of sine, plus sine t minus 2 sine cubed t. This will be 2 sine t minus 2 sine cubed t plus sine t minus 2 sine cubed t. So y is equal to 3 sine t minus 4 sine cubed t. So we've got everything now in terms of sine t, right? Because we have x is equal to 1/3 sine t. So using that x is 1/3 sine t, we can get that sine t is equal to 3x, which I can now substitute into the y formula. So we'll have y is equal to 3 times 3x minus 4 times 3x cubed. So they want it in this form here, so they want to take something out. So they both have 9x in common, so I can get 9x out. And then we'll have 1 minus 12x squared inside the bracket. So this will be our Cartesian equation. So as you can see, it's slightly different. Rather than substituting straight away, we use an identity to make it easier for us to substitute. Right. B, state the domain and range of y is f of x. So finding the domain and range is the same thing. We have to find the ranges of the parametric x and the parametric y. So let's start off with the parametric x. So x is 1/3 sine t. Like before, it's best to just sketch it so you can visualize it. So we'll have, it's just a literal sine graph, but it's just times 1/3, meaning the y values are times by 1/3. So it's going to look something like this. We have 1/3, and this is negative 1/3. But we are given a certain domain for t. It says earlier that t is between 0 and pi/2. So this we need to take into account of, because this is 0, this is pi/2. So the possible x values will be from 0 to 1/3 only. So it can't be any negative answers. So this here is going to be the domain of our function or our Cartesian equation. Right, for the range, we just have to use the y parametric equation. So y was equal to sine 3t. And we just have to sketch this one now as well, just to visualize it. So sine 3t, meaning that it's going to just get shrunk by 3, a factor of 3, in the x direction. And we need to identify, or this is going to be still 1 and minus 1. We need to know where pi/2 is, right? Because once again, t has a certain domain. This is going to be t here and y here. So t, this is going to be pi/2, so it's going to be roughly here. So therefore, we can say, oh, y can take any value, right? So y is going to be between -1 and 1, let's say. And that's it. That's how you would go about dealing with parametric equation when we have trig terms. Let's just try one more. So a curve has parametric equations: x is tan squared t plus 5, y is 5 sine t. So find the Cartesian equation first. So they've said, first of all, we looked at the two trig terms and we try and think of an identity that involves both of them. Well, tan t is equal to sine over cos t. We know this one. Yeah. But it's also tan squared, right? So an identity that involves tan squared would be the 1 plus tan squared is sec squared t. So we can use this one here, right? Because sec squared is 1 over cos squared, and cos and sine, we can relate them together. So looking at here, we have that sec squared t is 1 plus tan squared, and tan squared t is equal to x minus 5. So it's going to be 1 plus x minus 5, which will give us x minus 4, which is sec squared t. So sec is 1 over cos, right? So I can say that cos squared t is equal to 1 over x minus 4. And we know that sine squared t plus cos squared t is equal to 1. So sine squared t will be equal to 1 minus cos squared t. So sine squared t is equal to 1 minus 1 over x minus 4. Okay, and we can see here that y is 5 sine t, right? So y is 5 sine t. And because they want y squared, you can say that y squared is 25 sine squared t. And because we found sine squared t already, this is going to be equal to 25 times 1 minus 1 over x minus 4. So this here will be the Cartesian equation. As you can see, I've used an identity to make sure that I can substitute those two parametric equations together. Right, B, determine the possible values of x and y in the given domain of T. This just means find the domain and ranges of the Cartesian. So once again, we just sketch each one. So first things first, x is tan squared t plus 5, where t is between 0 and pi over 2. So for this one here, we haven't really learned how to sketch a tan squared graph, right? So in this case, it's not rather sketching, we should try and visualize it. So if I was to draw a tan graph here, and t is between 0 and pi over 2. Okay, so pi over 2 is an asymptote, right? Like this. And so if we're squaring any values within that range, then they're all going to be a positive value, with it being bigger than 0, and having no upper limit because it's an asymptote, it's going to go up into infinity. So in fact, this will be x, so x is just going to be bigger than 0. So that's going to be the domain of the function. Secondly, for the range, we can say y is 5 sine t. This is a slightly more easier graph to sketch. So we'll have a y-axis, an x-axis, a t-axis, sorry. So I'm just going to look at a sine graph, where this is 5 and minus 5. T is between 0 and pi over 2, so pi over 2 is between here, right? And this is 0. So y has to be between 0 and 5. So this here will be the range of the Cartesian. So as you can see, it's the same concepts as we've been learning before, it's just dealing with the trig terms. And we do that by using the identities we've learned in the previous two chapters.